What's up, everybody? It's Dan from SageMathTutoring.com, and we have a video covering inverse functions and the derivative of inverse functions, basically. And more specifically, it's the derivative of inverse functions at a particular x value. Now, this is a concept that I have less familiarity with. I was working with a student on this stuff recently, and I felt the need to sort of research it a little bit further, and I wanted to make this video. So, anyway, here we go. It's really all about this formula right here. If you want to take the derivative of an inverse function at a particular x value, then you're just going to rely on this. Now, if you notice that this is kind of gobbledygook, this looks a little crazy, but I did some color coding so you can very clearly see that, well, first you're going to want to find the inverse function of f of a, right? Then you're going to worry about, okay, well, that's going to produce a number. It's going to produce a number. And then you're going to find the derivative as it relates to that particular number. So in a way, it's almost like a two-step process. If you think about it, it's really not that bad. Even though this looks confusing, you do the blue part first, and then you worry about the red part. Okay? So for something like problem number 1, which is right here, right? Problem number 1, we'll move things around a little bit. We have this scenario where the original function is f of x equals x cubed minus 1, and the b is 7 in this case, so we could say a is 7. I'll use b to avoid confusion, actually. Might as well do that. All right, let's avoid confusion here, just to conform this formula to the worksheet. All right. So the b is 7 in this case. So ultimately what we're trying to find, according to the blue part, is the inverse of f of 7, right? Now, let's think about it, right? Because we want to get this blue part first. Let's think about it. Well, the inverse of f of 7 is literally whatever x is when this function is set equal to 7, okay? So that's how you find the inverse of f of 7 is by setting the original function equal to 7 and solving for x. So I'm going to do that right here. We're going to have 7 equals x cubed minus 1. And we're going to have x cubed equals 8. And x clearly equals 2. All right? So what that means is the inverse of f of 7 is 2. All right? So we just found our awesome number that's going to go here, right? So if you think about it, you could sort of update the equation where it's like 1 over f prime of, in this case, it's 2. So now it's very obvious what our next step is, right? We went from here to here. So that's very obvious what our next step is. Our next step is to find the derivative of f at 2. Well, finding the derivative of f is pretty easy. That's going to be a matter of just taking the derivative of the original function. All right? So it's going to be 3x squared. And more specifically, we want that at 2. So that's going to be 3 times 2 squared, which is 12. So ultimately, this is going to be 1/12 at the end of the day. Hopefully that makes sense. All right, so not too bad when you have the formula in front of you and when you have color coding at your disposal as well. That kind of helps, right? So that is that one. Looking at, let's see, the next one here, problem number 2. So we'll just move this here, move this here. We'll kind of do the work in the box here. So clearly we're going to be setting up the following formula. Probably a good first step to just write this. You know that what we're dealing with is this, where b is 2 this time, right? And then that can sort of serve to remind you that this is the thing we need to find first. And remember, that's nothing more than setting the original function equal to 2 and solving for x. So we're going to do that right now. We're going to set it equal to 2, solve for x. Now what we can do at that point is subtract 2 from both sides. And then you're going to have this interesting situation here. Now, when I was working with my student earlier, there was a question as to how would you factor this, because we have a degree of 3, it is a trinomial. Well, unfortunately, as far as I could tell, you would have to use the rational root theorem. And the rational root theorem basically says that the possible rational roots of this would be all the factors formed by the constant over all the factors of the leading coefficient. So all the factors of the constant at the end, -3, would be plus minus 1 and 3, and all the factors of the leading coefficient are literally just plus minus 1. Now, in a way, it's redundant to say plus minus plus minus. You can literally just say, okay, all the potential rational roots would include plus minus, let's just say 1 over 1, which is just 1, and then let's just say 3 over 1, which is 3. So in a way, you could just kind of reduce it. Now, how do you know which of these rational roots actually work when it comes to this thing? Well, that's when you would use synthetic division. So synthetic division would take into account really this scenario where it's really, x cubed plus 0x squared, don't forget that, plus 2x minus 3, because we want all of those coefficients represented, or all the exponents represented, I should say. So then we're going to have 1, 0, 2, and -3. And then what you do is you just plug in the potential rational roots. Let's start by plugging in, let's say 1, because that's kind of easy, right? So how does this work? You would bring that 1 down. So you have a 1 here, and then you have 1 times 1, which is just 1. And then you're going to be adding 0 plus 1. 0 plus 1 is just 1. Then you would say 1 times 1, which is just 1. And then you would be adding 2 plus 1, and that's going to be 3. And then you're going to have 1 times 3, which is just 3. And then you're going to be adding -3 and 3, and that's 0. Now, actually, what we have proven is that 1 is an actual root for this particular equation, meaning if x equaled 1, then this equation would indeed equal 0. So we actually found our rational root. Now, what that also means is that if we were to factor this equation, what that also means is that you can factor it where one of the factors literally would be x minus 1, because that would be the parentheses that gives you a solution of 1. Okay, so it would be that. And then the question is, well, what's left over here? Well, what's left over here is all this stuff, okay? Now, what do I mean by that? Well, these are the coefficients of the next factor. So the coefficients are 1, 1, and 3. And as far as the degree, it's going to be a degree of 2. It's always 1 less than the previous degree. So we have 1 times x squared plus 1 times x plus 3. And then you are done with that. So we have officially factored this scenario. Now, clearly, one of the roots is 1, right? So we could say that we found our x. Now, when you look at this, you might be wondering, well, maybe there's another root that's associated with this. Well, you would see after investigating the discriminant here, b squared minus 4ac, that the discriminant would be negative, and therefore the only roots associated with this particular factor would be imaginary. So therefore we can just disregard those roots. The only root that we really need is x equals 1. Okay, so hopefully that makes sense. So what does that mean for our problem? Well, we just found the inverse of f of 2. It is 1, right? Because how do you find the inverse of f of 2? Well, you set the original function equal to 2 and you solve for x, right? So we now have our, we could say, we now have our blue number now, right? We now have our blue number. So let me rewrite it. So we know that where we are now is we have f prime of 1, right? Because that's what it was 1. So now it's going to be the derivative of the original function, and now we're plugging in 1 for x. It's just as simple as that. Now the derivative of the original function is going to be 3x squared plus 2. We are now plugging in 1 for x, and that would be 3 times 1 plus 2, which is 5. So therefore, the final answer at the end of the day is 1 over 5, and that is the answer. All right, looking at the next one, which looks like it features some trigonometry stuff. So now we have f of x equals the sine of x, and b is equal to 1/2. Now, I think my student is probably getting the hang of the process. For those of you watching, you're probably getting the hang of the process. So we're going to leave this here as a reference, but we're not necessarily going to go about it by figuring out the blue part first and then the red part. I'm not going to rewrite it in that way. We're just going to go about the algorithmic process. And we all know by now the algorithmic process is to literally set this equal to b and then solve for x, right? So we have sine x is equal to 1/2. Now, this is important. It says that it's on this interval from negative pi over 2 to positive pi over 2. Now, those of you who took trig should hopefully remember that what that really means is that we're dealing with the first and fourth quadrant, because what we're really taking into account are all the angles that go from negative pi over 2 to positive pi over 2. So it's like that. It's these angles. Now, I don't know if my student at home recalls, but the sine of angles are only positive, rather, I should say. See how the sine of x is a positive number? Sine of an angle is only positive in the first and second quadrant. So out of these two, the first or fourth quadrant, the only quadrant we need to pay attention to is the first quadrant, okay? Because 1/2 is positive, okay? Sine of x equals negative 1/2 would cause us to focus on the fourth quadrant. But since sine of x equals positive 1/2, sine is positive in the first quadrant. So we're going to focus here. Now, it is the case that x equals 30. Hopefully my student remembers that according to the unit circle perhaps, or using those little 30, 60, 90 triangles and the 45, 45, 90 triangles, depending on how my student sort of learned this, it is the case that the sine of 30 degrees is equal to 1/2, okay? So x is equal to 30, which means that we're now going to replace the blue number with a 30, right? And therefore, we're going to take the derivative of the original function at 30, all right? So the derivative of the original function, I think my student recognizes, is cosine, right? So that's cosine of x, and it's going to be cosine of 30, therefore. Now, the cosine of 30 is radical 3 over 2. So ultimately, the answer would be 1 over radical 3 over 2, aka 2 over radical 3, aka 2 radical 3 over 3. And that should be the answer to problem number 3. Okay, looking at problem number 4. So let's see what's going on over here. Problem number 4, we have f of x equals cosine of 2x and b equals 1. So once again, we're going to set this equal to 1. We have cosine of 2x equals 1. Now, hopefully my student remembers that the cosine, the angle, if you were to do the cosine of an angle and have it equal 1, well, that angle is 0, okay? Now, if need be, we could always look at the unit circle for this stuff. Like, here's the unit circle, right? Now, cosine is associated with x coordinates, right? Now, clearly we have an x coordinate of 1 right here, and that's associated with the angle of 0, okay? So therefore, we know for a fact that 2x equals 0, right? The angle 2x equals 0, and therefore x itself equals 0. So in a way, we just found our blue number. It's going to be 0 here, right? So now we have to figure out f prime of 0. Well, that's simple enough. You take the derivative of the original function, and then you plug in 0 for that. So the derivative of cosine of 2x is going to be negative sine of 2x, but this is a chain rule, because if it was just cosine of x, then the answer would be that the derivative is negative sine of x, but since it's more complicated than that, it's the cosine of 2x, you have to do the additional step of multiplying that times the derivative of what's inside the parentheses. In this case, it's 2x, and the derivative of that is 2. So we're looking at, we can say negative 2 times sine of 2x. Now that's the derivative of the original function. Now once again, we will be plugging in 0, right? We're plugging in 0 for x. So what we're really looking at is negative 2 times the sine of 0. Now the sine of 0 is 0, okay? Sine of 0 is 0 because sine is associated with the y-coordinate. And here's, the angle of 0. So the sine of this angle is associated with the y-coordinate here, which is 0. So therefore, this whole thing ends up being negative 2 times 0, which is just 0, right? So it turns out that this whole number down here is going to be 0. It's going to be 1 over 0, and that is undefined. So that's the answer to that one. Okay. If f of x, blah, 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 g is the inverse of f, then g prime of 10. Okay, so in my opinion, what they're doing here is they are just being tricky. It's still the case that we're using this format. It's just that now they're calling this g prime of whatever, all right? Instead of saying inverse of f prime of b, now they're saying g prime of b, okay? So it's still going to be the exact same protocol. Now, what is that protocol? Well, first of all, you got to get clear on what your b is. The so-called b in this case, right, is 10, and then you just follow through with the motions. So we're going to set the original function equal to 10 and solve for x. So clearly we have 8, we have 4 over x equals 8. X is going to equal 1/2, therefore. Now we're going to go ahead and take the derivative of this, and we're going to plug in 1/2 for x, and then we're going to have the number that goes down below. It's just as simple as that. So before I do the derivative of f of x, let's get clear that f of x is really 4 times x to the negative 1 plus 2. And then when I do the derivative, it's going to be negative 4 times x to the negative 2. And that's really negative 4 over x squared. Now we will be substituting in that 1/2 in for x there. So we're really looking at this scenario now. And that would be negative 4 over 1/2 squared. And that's equal to negative 4 over 1/4. And that's equal to negative 16. So that's the number that goes down below. It's going to be 1 over negative 16. So that's going to be the answer, also known as negative 1/16. So this is equal to negative 1/16. All right, so that's the answer to that one. Okay, so for problems like these, I'm going to give my student and you guys a very specific way of going about them that, in my opinion, is very organized and easy on the brain. All right, so here's the way. First of all, let's read it. If 3, 5 is a point on the graph of an original function f of x, and f prime of 3 equals 2, then which of the following must be true? Now every answer choice is sort of asking you to provide information about the derivative of the inverse of f of whatever, okay? So here's the way I strongly recommend going about it. And this is partly inspired by this table I see down here for a future problem. What if we sort of used tables like that and helped our life as a result, okay? For example, you can set up a table that pertains to the original function f of x, right? Here it is, f of x. And you just fill in the information that they give you. Clearly when x is 3, y is equal to 5, f of x equal to 5, and apparently f prime of 3 is equal to 2, all right? Now what I'm going to propose is get used to using these tables. It's kind of a shortcut approach, I would say. Get used to using these tables such that you can now create another table, only this time with the inverse of f of x and the derivative of the inverse of f of x, all right? Now, what do we know about the inverse of f of x? Well, it's going to be the same x, y coordinates, except they're going to switch, 5 and 3. Now, this thing, you could use this structure and rely on all the information that's present within these two tables to figure out what the derivative of the inverse of f of 5 would be, okay? If a was 5 in this case, right? Because it's 5 right here. It would be 5 right here, right? But I'm just going to give you the shortcut. The shortcut of the century is it's going to be this number in the denominator, all right? That's the shortcut of the century. So you could always make a table that pertains to the original function, and you could always very easily make a table pertaining to the inverse of the original function, and at least fill out one row. If you have one row filled out here, well, guess what? You can fill out a row here. Now, once again, the fact that this is 1/2 could be proven by relying on this structure. If my student at home wants to do that, you could always just substitute 5 in for a, because that's the x value. Put 5 down here. Figure out what is the inverse of 5. Well, that is 3. What's f prime of 3? Well, f prime of 3 is right here. It's 2. So this denominator is going to be a 2. I don't know if you followed that, but you could prove it using all the available information. Now, I'm going to say go ahead and get used to the shortcut, though, because this shortcut is actually going to come in handy with this next problem, all right? This next problem is giving us a whole bunch of gobbledygook. F of 3 equals 8. F prime of 3 equals 5. What do we know about f of, inverse? Well, I don't know. Let's flesh out one of those darn tables. I'm going to flesh it out right here. We got x, we got f of x, and we got f prime of x, right? Apparently, when x is 3, f of x is 8, and apparently f prime of 3 is 5. Okay, wow, cool, great. Now they're like, what do we know about f inverse of f? I don't know. Let's fill out the table and let's see what we can figure out about the inverse of, f. So let's do this. This is always kind of weird, this part. It's like a prime, right? All right, so I'm going to fill out the table based off of this row. Well, guess what? We got an 8, we got a 3, and you know what we have? 1/5. That's what we have there due to the shortcut. Done, right? So what do we know about f, inverse f? Well, what we know is that a point that exists on inverse of f is a3. So we know that, right? We definitely know that. But what else do we know? Well, we also know that, if we were to do the derivative of the inverse of f at 8, right? At 8. Well, guess what? That would be 1/5. So we know that as a fact. So in other words, the slope of the tangent line on this function, when x equals 8, is 1/5. So that's something you could say. Notice how we batched this information together based off of the new table. All right, so hopefully that makes sense. Problem number 8, let f of x equals that. Let g be the inverse function. Evaluate g prime of 0. Cool. So I think this is much like the earlier problems, right? G prime of 0. The so-called b in this case is 0. So we're going to set the original thing equal to 0, and then we would have to solve for x. So that is, once again, a, unfortunately, rational root theorem situation. So we're looking at plus minus 1 and 2 as the potential rational roots. I'm going to plug in 1 into synthetic division. So we're going to have 1, 0, 1, negative 2. Remember that the red 0 is a result of a 0x squared here, right? So that's the coefficient for the 0x squared. Dropping down the 1, 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, 1 plus 1 is 2, 1 times 2 is positive 2, and that is a 0 there. So we know for a fact that one of the actual rational roots happens to be 1, which means that this thing can most definitely be factored as x minus 1 times something. Well, what belongs in the longer parentheses? Well, it would be based off of these coefficients. We have 1, 1, 2, and you always drop down the exponent. So it's going to be 1 times x squared plus 1 times x plus 2. Now, obviously, x equals 1, right? X equals 1. So that's nice to know. Looking at this, if we were to set this equal to 0, you would quickly see that the discriminant would be negative, which would produce imaginary solutions. So therefore, we could disregard this parentheses. Okay, the discriminant is b squared minus 4ac. If we did b squared minus 4ac with this, you would get a negative number. Anytime the discriminant's negative, that means that your solutions would be imaginary solutions. And in that case, we could discard this. So the only solution we need to worry about is x equals 1. Now, as you may recall, what we then have to do is we have to take the original function, take the derivative of it, right? And then we're going to plug in x for 1, and that gives you the number that goes in your denominator, right? So that's going to be 3 plus 1, which is 4. So ultimately the answer to this, to g prime of 0, is 1 over 4. All right, hopefully we can make sense out of this thing. Let's see. A function f and its derivative taken on the values shown. G is the inverse of f, find g. All right, so check it out. I'm going to literally make an entire table for f, the inverse of f. Right, and then we're going to do the derivative of the inverse of f. Now keep in mind, they're telling us that g is the inverse of f, so up above it, I'm going to say that we could say that this is also known as g of x, and we could also say that this is g prime of x, right? I'm just kind of using f to show that this column is just the inverse of whatever. So we are trying to find g prime of 6, right? We are trying to find g prime of 6. So let's flesh out 2 rows on this thing, because we know for a fact that there's 2 rows here, which means we could fill out 2 rows here. So, of course, one of the rows is going to say 6, 2, and then it's going to be the reciprocal of that, right? It's going to be the reciprocal of that. So it's 3, right? Isn't that what we've been doing with the previous tables? We take this number and we flip it upside down, or we do the reciprocal of it, right? So that's just 3. Over here, we're going to have 8, 6, and then 2/3, right? I feel very comfortable with that. At the end of the day, we want g prime of 6. We want g prime of 6. Well, that's this row. G prime of 6, yeah, guess what? It's 3. Done. Notice how all we had to do is rely on that previously mentioned skill of fleshing out a table that pertains to the original function and the derivative, and a table pertaining to the inverse function and the derivative. The first 2 columns are very easy. Just switch these. And the next column is very easy. Just find the reciprocal of that one, and then you're good. All right. This is sort of switching gears a little bit. We just want to find the derivative of these functions. Remember to use logarithmic properties before differentiating. Okay, cool. Remember to use logarithmic properties. Here's what I know. I know, and I just told my student earlier today, that if you have an original function where it's like some constant raised to an x, then the derivative of that is ln of the base, the constant base, times a to the x again, all right? I would say that that's just simply worth memorizing, all right? Because that makes things very easy. So if we want f prime of x, well, guess what? It's going to be ln of 5 times 5 to the x again. And that's it. That's all there is to that one. Let's see. Okay, looking at the next one. Well, the reality is that you can do the next one in the exact same way. All right. Now I'm going to demonstrate that. Now my student who's watching, we had talked about how the teacher actually went about this in a slightly different way, but I'm going to prove that our way leads to the same answer as what the teacher says. All right. Now we're going to cover the way that I've been doing it first, and then we'll cover the way the teacher did it, and then I'm going to prove that it's the same. So how have I been doing it? Well, y prime is going to be ln of 4, right, times 4 to the 3x, except now it's a chain rule situation, right, because it's not just an x up here, it's a 3x, so we have to do the additional step of multiplying times the derivative of 3x, which is 3, right? And ultimately, that would be the answer. You could be nice and put the 3 out front, maybe. We have this scenario right here. It's kind of a chain of multiplication, all right? Now, my student's teacher did something slightly different. What the teacher did is she took the original situation, which is 4 to the 3x, and she or he, I think it's a she, then converted 4 to its sort of base, which is 2 squared. So it's really 2 squared of 3x, and that's really y equals 2 to the 6x. And then what my student's teacher did is then she did the derivative of that, right, in the same fashion though. So it's ln of 2 times 2 to the 6x times the derivative of 6x, which is just 6, and then that's going to be 6 times ln of 2 times 2 to the 6x. Now, let's be very sort of meticulous here. It is the case that 2 to the 6x could be rewritten as 2 to the 6th raised to the x. Now, 2 to the 6 is 64. So really it's just this, times 64 raised to the x. So that's the final answer that my teacher gave. Now, what I want to show my student is that her final answer is actually the same as my final answer. I'm going to prove that by setting them equal to each other. We're going to have my answer right here. All right, 4 to the 3x. And her answer right here. Times 64 to the x. Now, right away, I'm looking at this, and I'm suspecting that this is going to be the same as this. And sure enough, it is. Because 4 to the third is 64. So that's really 64 raised to the x power, which means that we can sort of cancel these. So now the real question is it the case that 3 times ln of 4, is that equal to 6 times ln of 2? That's a little bit trickier, right? It's kind of weird looking. Well, hopefully my student remembers that you could always put that coefficient as the exponent. So what that results in is on the left, ln 4 raised to the third, right? Because you could do that with logs. And then you're going to have ln of 2 raised to the 6. So now the question is, okay, well, is 4 to the third the same as 2 to the 6? Well, actually, yes. 4 to the third is 64. And, you know, I should wedge this in because this is the real question. 64 equals 64. 2 to the 6th is also 64, so that's how that works. The answers are the same. For my student who's watching, I don't know, if you want to kiss your teacher's butt a little bit, just replace, you know, anytime you have a base that could be reduced to a lower base, then go ahead and do that first and then simplify in that manner and then take it from there. Maybe that's your teacher's style. Maybe that's more of an official way that I'm not familiar with, to be perfectly honest. So looking at this one, still going to be a matter of relying on the same sort of structure of derivative, right? So the derivative of anytime you have a constant base like that, well, it's going to be ln of that constant base times the original thing. Except now we have to recognize that it's a chain rule, so we have to multiply that times the derivative of the exponent, right? So that's going to be 2. So that is the answer to problem number 13, believe it or not. Okay, problem number 14. Okay, so this one is a chain rule, or a product rule, I should say. It's probably a chain rule too, but it's a product rule. All right, let me just get rid of this stuff real quick. Get it out of here. So we have a function which we'll call u times another function which we'll call v. Now, hopefully my student remembers that the product rule says that if you have an original function called u times v, then the derivative of that would be u prime times v plus u times v prime. All right, so therefore, perhaps off to the side, it would be helpful for us to figure out what that is. U is equal to x, u prime is therefore equal to 1, v is equal to 7 to the x power, v prime is therefore equal to ln 7 times literally 7 to the x. It's actually very simple. So all you have to do is then use the product rule, which says that it's going to be u prime times v. Okay, that's going to be 1 times 7 to the x plus u times v prime. So that's going to be x times, what's v prime? ln 7 times 7 to the x. ln 7 times 7 to the x. That is the answer. Now, it's possible my student's teacher had it in the reverse. Maybe the teacher did u v prime first times u prime v, but ultimately this is going to be the answer either way. We once again have a product rule on our hands. Let's get very clear. Y equals u times v. Then y prime would be u prime times v plus u times v prime. So let's say that u is equal to x, therefore u prime is 1. We're going to say v is equal to 3 to the negative 2x, therefore v prime, and we're going to be very careful, it's going to be ln 3 times the original thing, which is 3 to the negative 2x, times the derivative of that weird exponent, negative 2x. Well, that is negative 2. All right? So that's how that works. So it's going to be y prime equals u prime times v. Well, u prime is 1. V is 3 to the negative 2x. Plus u times v prime. Well, u is x, right? V prime is the whole gobbledygook mess. ln of 3, 3 to the negative 2x, and negative 2. So that is that one. The final answer, for the record, doesn't need that 1 there, right? It's also the case that there are common factors here. So if you wanted to, you could factor out 3 to the negative 2x, and you would have 1 plus, or actually 1 minus, I should say, 1 minus 2x times ln of 3. It's also the case that this thing could be turned into 1 over 3 to the 2x times that whole thing. Now, the 1 over 3 to the 2x thing, I'm going to wrap in green parentheses because I want my students to just be familiar with the fact that that can be represented in different ways. So for example, the reality is that's really equal to 1 over 3 squared to the x, which is really equal to 1 over 9 to the x. And that could be rewritten as 1/9 to the x. Now, why is that? Well, because the x could be applied to the top and the bottom. Well, it's clearly being applied to the bottom. There it is. But it could also be being applied to the top as well. 1 to the x is just 1 because 1 to the any power is just 1, right? So do be on the lookout for the answer being written as 1/9 raised to the x power, all right? If I was the teacher, I certainly wouldn't mind this. I don't even know if I would mind this, to be honest. I don't even know if I would mind this, but that's sort of up to the teacher, all right? All right, looking at the next one. Problem number 16 also looks like it's going to be a product rule. So in this case, we'll call the x squared u, and we'll call the 3 to the x v. And we could say that u is equal to x squared. We could say that v is equal to 3 to the x. U prime would therefore be 2x, and v prime would therefore be ln of 3 times 3 to the x. All right, so that one's going to be very straightforward. The derivative of that is going to be, remember, the derivative would be u prime v plus u times v prime. So the derivative of this thing is going to be u prime times v, which is going to be 2x, times v itself, and v is 3 to the x. And we're going to be adding u, which is x squared, times v prime, which is ln 3 times 3 to the x. Now, in my view, that is the answer. However, do be on the lookout for the fact that there is a GCF here, and you could always factor that out. So do not be surprised if you see the final answer in a textbook or something represented like that. All right. But that is the answer to that one. Problem number 17, I would say that's a quotient rule as far as I could tell. So if it's the case that you have y equals u over v, then y prime is going to be v squared on the bottom, v times u prime, minus v prime times u. So once again, just sort of writing down the u and the v. U would be 5 to the 2t. The v would be just t itself. And u prime is therefore going to be ln of 5 times 5 to the 2t. But this would be a chain rule scenario because it's not just 5 raised to the t, it's 5 raised to the 2t, which means we have to do the additional step of multiplying by the derivative of that exponent 2t. So that's going to be 2. Now, let me just clean that up a little bit. I'm going to put the 2 out front. We have 2 times ln of 5 times 5 to the 2t. All right, handwriting is kind of small, but you get the idea. V prime would be 1. So then it's really just a matter of plugging in the information after that. So clearly we're going to have t squared on the bottom. It's going to be t right here because that's v itself, and then u prime is the expression that we discussed, 2 times ln of 5 times 5 raised to the 2t. All right, and that's going to be minus, let's see, v prime times u, so that's going to be 1 times the original u, which is 5 to the 2t. Now, it is the case that really this is just sort of 4 numbers being multiplied together. We have t times 2 times ln of 5 times 5 to the 2t. So, you know, even though I wrote the parentheses like this, that's still the reality of what's taking place here. So one way of sort of working with this is you could factor out the 5 to the 2t, right? So that's a possibility. So don't be surprised if you see the final answer represented like that, perhaps in a textbook or something. So it's going to be 5 to the 2t times, let's see, we're going to have 2t here times ln of 5 minus 1, and that's t squared. Now, it's also the case that 5 to the 2t, if you were to sort of investigate that a little further, that is actually 5 squared raised to the t, aka 25 raised to the t. So just be on the lookout for that as well. The reality is that this is 25 raised to the t. So just recognize that the final answer could be written that way as well. If I was the teacher, I would be fine with this as the final answer. I would also probably be fine with this as the final answer because I don't see the need necessarily to factor out the GCF because it's not like we're canceling anything here. I would say it's worth factoring out the GCF just in case you could cancel something, but it turns out that you cannot. Okay, so looking at this one, it certainly looks like it's going to be a product rule scenario. And one of the things that's potentially confusing about this is that instead of an x, we're using theta, but don't be thrown off by that. Theta is just a symbol that often symbolizes an unknown angle, okay? An unknown angle. So what we're going to do is just really the same thing that we would do if it was just like an x or whatever. This is clearly going to be a product rule. You have u and you have v. So we'll write that off to the side. U is equal to 2 raised to the theta. V is equal to cosine of pi times theta. And u prime is clearly going to be ln of 2 times 2 to the theta. That's all there is to that one. This is not a chain rule scenario. Imagine that that was just an x. Well, it would be ln of 2 times 2 to the x, right? So it's not chain rule because that's just a variable. There's not an actual function up here other than theta. So as it pertains to v prime, we are certainly looking at negative sine of, you know, the angle. But then since it's not just theta in here, it's a little bit more complicated. We have to do the additional step with the chain rule of multiplying this by the derivative of what's inside the parentheses here. So the derivative of pi times theta is literally just pi. Now, keep in mind, pi is just a number. It's like 3.14 something, right? Pi is not a variable, even though we're using a symbol to represent it. It's still just some number. I'm going to clean this up a little bit. We're looking at negative pi sine of, you know, pi times theta. Okay, so at that point, product rule would be a matter of remembering that y prime is going to be u prime times v plus u times v prime. And in this case, we would be dealing with, f prime of theta is equal to u prime, which is ln of 2 times 2 to the theta, times v, and v is cosine pi theta, plus u times v prime. Now u is 2 raised to the theta power, and v prime is negative pi sine pi theta. Negative pi sine of pi theta. All right, cool. So at this point, I'll simplify a little bit further. We have ln of 2 times 2 raised to the theta times cosine of pi theta. And I'm going to say minus 2 raised to the theta pi sine of pi theta. Now we do have a GCF here and here, so you could hypothetically factor that out if you wanted to. We're looking at 2 raised to the theta ln 2 cosine pi theta minus pi times sine of pi theta. And really I should be wrapping that either in brackets or parentheses. Okay, problem number 19 looks like it's going to be a product rule scenario once again. So we'll call this U, we'll call this V, and let's sort of figure out what everything is up here. U is going to be 4 to the negative, I'm going to say negative 1/2 x. V is going to be sine of 2x. Now, U prime is going to be ln of 4 times 4 to the negative 1/2 x times the derivative of negative 1/2 x, which is negative 1/2. V prime is going to be cosine of 2x times the derivative of 2x, which is just 2. Okay, so at this point we can keep in mind that the product rule says that it's going to be u prime times v plus u times v prime. So let's go ahead and work that out. We have h prime of x is going to be u prime times v. So u prime is negative 1/2 ln of 4 times 4 to the negative 1/2 x. And that is what? U prime, right? Times v. So that's going to be times v, so we have to multiply that by sine of 2x. And then we're going to be adding u times v prime. Now u is 4 to the negative 1/2 x, and v prime is, we could say 2 cosine of 2x. All right. Now, we do have GCF here, so we could take out that 4 to the negative 1/2 x. And what we would end up having is negative 1/2 ln of 4 times sine of 2x plus 2 times cosine of 2x. Now, it is the case that 4 to the negative 1/2 is really, we could say, let's just analyze it up here. 4 to the negative 1/2 x is really 4 to the 1/2 raised to the negative x, and that's really 2 raised to the negative x. So it is possible to turn this into a 2 raised to the negative x. So that should do it. You could always reverse the order if you want nothing, but if you want it to be a little less annoying looking. So we could say that we're looking at this as the final answer. Although I'm looking at, when I check the teacher's answers, she's doing something interesting where it does seem like whenever we have a coefficient in front of a logarithm, we could analyze that off to the side. So that's going to be negative 1/2 ln of 4. Now that could be negative or minus ln of 4 raised to the 1/2 due to properties of logarithms. And that would be minus ln of 2 because really, 4 to the 1/2 power is really the square root of 4. So that's going to be minus ln of 2. So that's a possibility as well. You could always just call that minus ln of 2 and then sine of 2x. So it seems like the teacher is finding that to be important. So for my student who's watching this, just know that in your final answer, be on the lookout for any coefficients in front of the logarithms and perhaps apply those as exponents. Okay, so that's that. Let's see. This next one. So this next one requires us to understand that if you just had, a normal sort of logarithm scenario, like y equals log with a base of a of x, well, the derivative of that, and this is something you should memorize, is going to be 1 over x times ln of the base a. Okay, so that is exactly what we're going to do here. We're going to say y prime is really 1 over x, meaning the quantity that's being logarithmed right there. Okay, it's going to be 3x plus 1 times ln of the base. In this case, it's 2. Now, that is the structure, that we're supposed to use. However, this would be a chain rule scenario because we have a 3x plus 1 as opposed to merely an x there. So you have to do the additional step of multiplying by the derivative of 3x plus 1, which is just 3. Now, a nice way of writing that final answer would be to have the 3 on top, and then we would have 3x plus 1 times ln of 2. All right, so that's that. Looking at the bottom, it would be a matter of relying on the exact same structure, and that structure is here, right? So if we were to use that, we'd be dealing with f prime of x is equal to 1 over x squared minus 4x in this case times ln of 3, but it is a chain rule, so we'd have to multiply that by the derivative of x squared minus 4x, which is 2x minus 4. So we could rewrite the whole thing as 2x minus 4 on top, all over x squared minus 4x down below, times ln of 3. There is always the possibility of factoring out a 2 up here, but I'm not so sure how much that matters. Looking at the next one here, and we'll keep this as a reference. Right, so this one is, we could say challenging in the sense that there's that exponent hovering above. I'm going to say let's bring it out front right away. That's going to make our lives easier probably. So we have 3 times log the base of 4 x squared plus 1. Now what I would prefer to do is just, keep the 3 sort of on the outside and just find the derivative of this, and that should give you the answer. So if we were to do it that way, it would be g prime of x is equal to 3 times, let's see, we have 1 over x squared plus 1 times ln of 4 in this case, and that's going to be times the derivative of x squared plus 1, which is just 2x right? So that's going to be that. And if we were to kind of make it look nice at the end, we would have a 6x on top all over x squared plus 1 times ln of 4 down below. Okay, so that's the answer that I would offer. However, once again, looking at the teacher's answer sheet, it looks like the teacher decided that even ln4 should be represented as ln2 squared, which is really 2 times ln of 2. And that would pave the way for a cancellation, so I can kind of see the reasoning behind that. I'm not used to that, but according to her, it would be 2 times ln of 2, and that would turn that into a 3, and then we would have 3x up top times x squared plus 1 ln of 2. Okay, so I guess the moral of the story is, even when you've whittled it down to this moment, always double check and just ask yourself, okay, is there a way to create an exponent here that I could bring out front, essentially? So that's something to look at with each problem. All right, so let's see, bringing all of this over. Looking at this guy, let's immediately rewrite it as log with a base of 3 of x squared plus 1 to the 1/2 power. It is therefore the case that we could bring that 1/2 out front. So we have log base 3 x squared plus 1. At that point, we're ready to go with the derivative. Y prime would be, we always put something in the numerator, so rather than writing 1 up there, I'm just going to leave it blank for now. Down below, we have x squared plus 1, and it's going to be, oh, by the way, we got to have that 1/2 out front. I should not have forgotten that. So we're going to have x squared plus 1 down below times ln of 3. Now, we're going to multiply the top by the derivative of x squared plus 1, which is just 2x. Now, the denominator of 2 is going to cancel with that. So for this one, we should end up with just x over x squared plus 1 times ln of 3. And that's y prime. Now, just double checking, is there any exponent that we could create above that 3? No. So we move on. Looking at problem number 24, bring this over as our reference. Okay, in this case, it's going to be log base 2, 2x minus 4 raised to the 1/3. That 1/3 can go out front. So we have this, and then we'll just proceed in the exact same way. So we're looking at y prime is equal to 1/3 times 2x minus 4 times ln of 2, and up top is going to be the derivative of 2x minus 4, which is just 2. So at the end of the day there, we're going to have 2 over 3 times 2x minus 4 times ln of 2. And when I look at this natural log here, I do not see an opportunity to extract any exponents. So therefore, there's nothing to be done there. However, there is the GCF of 2 that could be taken out of 2x minus 4. So really, this whole thing could be rewritten as 3 times 2 times x minus 2 times ln of 2. And therefore, the 2's could cancel. And then we have 1 over 3 times x minus 2 times ln of 2. So that should be the final answer. Okay, so, well, we're certainly going to be taking the derivative of this thing at some point, right? So I'm going to say, let's just go off to the side and do that. So we have x squared over x plus 1, and if we were to do u prime, that would be x plus 1 squared, x plus 1 times the derivative of x squared, which is 2x, and it's going to be minus x squared times the derivative of x plus 1, which is just 1. So that's going to be 2x squared plus 2x minus x squared all over x plus 1 squared. And that's going to be x squared plus 2x all over x plus 1 squared. All right, so that is going to be important soon, okay? So when you do the derivative, it's going to be that same deal where if your original thing is this, then the derivative is going to be 1 over x times ln of a, right? So that's what we're going to do here. We're going to have f prime of x is going to be certainly some numerator, right? Some numerator. But down below, it's going to be literally x squared all over x plus 1 times ln of 2. Now, in the numerator, we're going to have this green box, right? So in the numerator, we're going to have x squared plus 2x all over x plus 1 squared. Okay, so that is hugely annoying, right? Because we have a fraction and a fraction up here, fraction down here. So what I'm going to do is a method where I get rid of I call them the mini denominators, and the miniature denominators are the x plus 1 squared and this x plus 1 here. And what we could do is we could multiply the top and bottom by the least common multiple of the miniature denominators, and that would be x plus 1 squared. So we're going to multiply the top and bottom by x plus 1 squared. In doing so, these will cancel entirely, and this x plus 1 entirely will cancel, leaving only one single x plus 1 up top. So we're sort of flattening out the numerator and denominator. So the numerator becomes x squared plus 2x, and then the denominator would be x squared times ln of 2 times x plus 1. So that's definitely one way of going about it. Now, when I look at the answer that the teacher gave, all right, because I like to just try these on my own first, and then check the answer that the teacher gave, she did something interesting, which I think is actually a pretty good idea. So what she seems to be emphasizing is really utilizing the properties of logarithms. So we have log base 2 of x squared minus log base 2 of x plus 1. Now, my way definitely worked because that is the correct answer. However, this would be a way, if you did that separation right out the gate, took advantage of the properties of logarithm, you could have avoided all of this, and you could have avoided having to do this special trick. And that's pretty good. So let's do it her way as well. F prime of x, in this case, it's going to be ultimately 2x over x squared ln of 2 based off of using this. I'm just going to kind of cut to the chase with it. Over here, we're going to have 1 over x plus 1 times ln of 2. And that's perfectly fine. It looks like the teacher then did an annoying step of finding a common denominator, though. Okay, so it looks like this problem is going to be annoying anyway. What she did is she recognized that, okay, the greatest common denominator, or the least common denominator that we could use for these is, of course, based off of the least common multiple of the two denominators, and this is the least common multiple of the two denominators. So you would have to multiply this thing by x plus 1 over x plus 1 in order to make it happen, and you'd have to multiply this thing by x squared over x squared in order to force that least common denominator down here. And then this would turn into the numerator, and you would have the least common denominator down below. So I'm not going to do that for my student who's watching. If you want, go ahead and just consolidate these. It's going to turn into that, and then take this first term, which is 2x times x plus 1, subtract x squared from it, simplify the numerator, and you would quickly see that you would indeed get that. All right. Either way, actually, even though I kind of like her way, it's still going to end up being such that you're going to have to do at least one annoying step like that, similar to what I did before. We're going to do it her way for problem number 26 because it's more of a priority to get used to the teacher's style. So this could be rewritten as log of x squared minus 1 minus log of x. Now, in this case, the base is 10. So the derivative would be 2x over x squared minus 1 times ln of 10 minus 1 over x times ln of 10. Now, if we were to get a common denominator, a good candidate would be the least common denominator candidate should be an expression that features like all the stuff that's presented. So x squared minus 1 needs to be represented, ln of 10 needs to be represented, but also x needs to be represented, right? So the only thing missing in the first thing is the x down below, so we're going to multiply the top and bottom by x. The only thing missing in the second term is x squared minus 1. So at the end of the day, we would have our least common denominator on the bottom, which is this. That's for sure. And then up top, we're going to have 2x squared minus the entire quantity. You got to be careful, wrap this in parentheses. The entire quantity of x squared minus 1. Now, that would be, I'll bring it over here, 2x squared minus x squared plus 1, which is going to be up top, I'll just put d for denominator. Up top, it's going to be x squared plus 1 over that denominator. So ultimately, the answer should be x squared plus 1 over x squared minus 1 ln of 10 times x. Okay, so looking at the last one, this happens to be a problem where you are apparently allowed to use a calculator, probably a graphing calculator, and that's a good thing because this is kind of a weird function and it is going to sort of require you to look at the graph. All right, now I'm not going to bring a calculator onto the screen here, but I'm going to walk you through what you would see if you did use a calculator. So first of all, it is the same process where you're going to find the inverse of g prime of 7, right? So it's going to be the same process that we did in the beginning where first you set the original function equal to 7, and then you solve for x. Now, we could subtract 7 from both sides, and you would have this right here. Now, what you would do is you would plug this into the calculator, and you would find where x crosses, or the graph rather, crosses over the x-axis. Now, I'll just give you sort of an idea. This graph looks a little bit like that, all right? And it crosses the x-axis at, I'm actually going to look out my calculator right now, 1.068 comma 0. All right, so therefore x equals 1.068. And then what you do, as you may recall, is you find the derivative, right? You find the derivative, and that's going to be 45x to the 8th minus 2x plus 2. And then you put in that 1.068 into the derivative, right? So 1.068, 1.068. And if you were to use your calculator and figure out what that is, that would end up being approximately 75.78-ish. All right. Well, actually, they want to 3 decimal places. So it's really 75.778 062 whatever. And then you can recognize that that's the number that's going to go in the denominator underneath 1. So keeping in mind its inverse is going to be 1 over that number. And then at the end of the day, that's going to equal, if we were to round it to 3 decimal places, that's going to equal 0.013. All right, so hopefully that makes sense. Kind of a long-winded video covering some pretty crazy concepts, but for my student who's watching this at home, hopefully this is helpful, and for the rest of you, hopefully it was helpful, and I will talk to you later. Bye.